Welcome to the presentation of a research called Experimental and Computational Characterization of Additively Manufactured Rotational Compliant Joints, a stacking strategy for adjustment of their equivalent stiffness, made by Espejo, Juan Urquizo, and Gonzalez. You can read more in our recent paper published in Results in Engineering journal. Our research works with compliant joints. Compliant joints are flexible structures capable of motion transmission with the deformation of their flexure hinges. They store the strain energy from the deformation and then release it to return to its original position. Compliant joints have a reduced rotational displacement compared to regular joints, which prevents them to be applied as energy storage components in medical or vehicular devices. However, their displacements can be increased by interconnecting multiple iterations of a same compliant joint into a more complex mechanism. Our solution is a stacking strategy for rotational compliant joints, capable of more than 100 degrees of rotation, keeping maximum torque and keeping maximum stress. Three different types of rotational joints will be characterized and tested in our strategy: multi-leaf, DR3, and semicircular joints. By using intermediate structures with prismatic pokayokis and screw holes, multiple stages of a same joint can be interconnected in a series of floors, leaving an upper and lower pokayoki for fixing and loading. Each iteration will add 25 degrees to the rotation of the mechanism, ending with a 100-degree rotation on a 4 iterations mechanism. Joints were manufactured using an illegal Saturn IV Racer printer machine. The material used was illegal standard resin 2.0. Finite element analysis was done using ANSYS Workbench software, and experimental testing was made using a Mark X torque analyzer machine. A single joint of each kind was tested first to analyze their torsional stiffness. Their stiffness was defined as the resulting torque divided by the rotation in degrees, ending with a higher stiffness in the multi-leaf joint, but also with a higher error percentage compared to finite element stiffness. The error percentage is caused by the stress distribution on the compliant joint structure rather than additive manufacture imperfections. As can be seen on screen, the manufacturer models keep the overall shape and details of the computational models. Then, assemblies of up to 4 iterations on each model were tested. Upon adding more iterations, the rotation increased, but a maximum stress remains similar, meaning that the equivalent torsional stiffness of the model is equal to the stiffness of a single joint divided by the number of iterations. Due to symmetry between joints, the stress and deformation on each iteration is similar. The error percentage of calculated stiffness compared to finite element was the lowest in the semicircular joint. Finally, the effect of the combined weight of the assembly was analyzed using finite element simulation on up to 7 iteration assemblies. As seen in the DR3 joint assembly as an example, the combined weight on the assembly produces a z-axis displacement, especially in the first iteration. This displacement on the already bent flexure hinges reduces the torsional stiffness further, at 4.78% in the DR3 assemblies, 3.96% in the multi-leaf, and 1.78% in the semicircular assemblies. Overall, we can conclude that our stacking strategy solution is effective for increasing the rotation of compliant joints, keeping their maximum torque and stress, and making them able for application on medical devices and vehicle components. This solution is limited by the dimensions of the whole assembly and the combined weight of their components. That makes that z-axis displacement. From all analyzed joints, the semicircular have the lowest error percentages and lower effect from combined weight. Thank you very much.